When you want to do mathematical operations including a force vector and a scalar quantity, you need to remember only one thing. Just consider the magnitude and keep the direction same as the direction of the vector. So do whatever operations using the magnitude and keep the direction same. Suppose you have, as shown in the figure, a force vector 40 kN that is making an angle 30 degree with the x-axis, and you want to multiply this vector by a scalar quantity. Suppose you are going to multiply this by 2. So the multiplication is simply multiplying the magnitudes, that is 2 into 40 will give you 80 kN, and the direction still the same as the original vector, that is 30 degree with the x-axis. If you are dividing force vector A by 2, that will give you 20 kN, 40 divided by 2, and that will give you 20 kN. Again the direction will be same, 30 degree with the x-axis. But the case is different when you are operating between two vectors. Then you need to consider both magnitude and direction. Suppose you have two vectors as shown in figure, A 80 kN acting along the x-axis and B 40 kN acting along the x-axis. So as you can see in the figure, these two vectors are acting in the same line, otherwise called collinear vectors. So A plus B will give you the mathematical sum of the magnitude of these two vectors, and the direction will be again the same. So A plus B is 80 plus 40, that is 120 kN, and the direction is same as that of A or B. And A minus B will give you again the mathematical difference between the magnitude of these two, 80 minus 40, that is 40 kN. Again the direction will be the direction of the biggest vector from these two. And because both of these have the same direction, the resultant direction also will be the same. But if you have vectors acting in opposite direction but collinear, then the resultant vector will have the direction of the biggest vector among these two. Now this is a case of collinear vectors. Suppose you have vectors acting at different angles with the same reference axis. Then you have to consider the magnitude, direction and the axis of these vectors. Suppose you have force vector F1 acting at an angle 30 degree with the x-axis, and another force vector F2 acting at an angle minus 20 degree with the x-axis. Here the magnitudes are different and the angles are different and the vectors are not collinear. So you are using the parallelogram law to find the resultant of this vector. You can also use the triangular law that we will find later on. But to use the parallelogram law, first you recreate your vector, first vector, that is force 1, F1, and then join the tail of the next vector to the tail of the first one. So you draw F2 here. What you need to remember here is keep the angles of the vectors same as original. So if this is a reference angle, then F1 will make same 30 degree with the x-axis, and F2 will make same 20 degree with x-axis. So as long as you keep the magnitude and the direction same, you can move the vectors anywhere in the space that we mentioned earlier on. So now that you recreated your first vector F1 and F2, what you need to do is complete the parallelogram by drawing parallel lines to these two vectors. So you draw a parallel line to F2 and you draw another parallel line to F1, and that will complete your parallelogram. Now if you find out the maximum diagonal of these parallelogram, that will give you the resultant vector. So this will be the resultant of force vector F1 and F2. And the angle of the resultant you can find by measuring the angle the resultant makes with the x-axis. And the magnitude will be the length of the resultant. You can also use a triangular law, which is kind of derived from the parallelogram law, to find the resultant of two vectors. Here you are connecting the tail of the second vector to the head of the first vector. In the previous case, both tails were joined together, whereas here you recreate your first vector and start the next vector from the head of your first vector. Again, you need to maintain the angles or the directions of the vectors. So draw your first vector and then the second one, keeping the angles same, and then join the tail to the head, and that will give you the resultant. Here again, you need to maintain the angles that the vectors makes with the reference axis. That is, you have to maintain these two angles. So force vector F1 should make the same 30 degree with x-axis here, and F2 should make the same 20 degree with the x-axis. Also, you need to make sure that you maintain the magnitude, the length of these vectors same. Now, as before, just measure the length of the resultant, that will give you the magnitude of the resultant, and measure the angle that the resultant makes with the x-axis, that will give you the direction of resultant. So this is just two vectors, and you find the resultant by either parallelogram or drawing a triangular. But in case if you have more than two vectors and you need to find the resultant of 3 or 4 vectors, then by successively using parallelogram law, you can find the net resultant force of a number of forces. In this case, where you have 3 vectors F1, F2, F3, which are acting at different angles to a reference axis, you can first use the parallelogram law to find the resultant of F1 and F2, and then use the parallelogram between the resultant of these two forces and F3. That will give you the net resultant of F1, F2 and F3. So what you do here is first find the resultant of forces F1 and F2 by using the parallelogram law. So first you construct a parallelogram connecting F1 and F2 and then find the resultant of F1 and F2. So let's call it R12, and then use this resultant and force F3 to find the net resultant. So first you find a resultant of F1 and F2, that is R12, and then you find the resultant of R12 and F3, that will give you the net resultant of R1, 2 and 3. So this is R1, 2, 3. And if you have another force, then just use R1, 2, 3 and the fourth force to find the resultant of all these forces together. So by successively using parallelogram law, you can find the resultant of any forces. Always remember, as long as you maintain the magnitude and the direction same, you can move the vectors anywhere in the space. But always make sure that you maintain the angles that the vectors make with the reference axis. So as shown here, you have a force F1 which makes an angle 30 degree with the x-axis. So as long as you maintain that 30 degree with the x-axis, you can move that vector anywhere. And you have another vector F2 which is making an angle 20 degree with the x-axis. Again, as long as you maintain the 20 degree with x-axis, you can move that vector anywhere. Also, you need to make sure that you maintain the magnitude or the length of the vectors same as the original. We discussed the force vectors and vector operations in the last couple of videos, and from this video onwards we are going to deal with the most interesting and important stuff of engineering mechanics, forces and moments. So what you are going to study in this video is resolving the force into two components, finding the resultants of a force system, a coplanar force system acting in a plane, and finding the net resultant force in a force system. So in the figure shown, you have got a force of 40 kilonewton acting at an angle 30 degree with the x-axis. So you have your axis system x and y and a force of 40 kilonewton. To resolve the force into two components, I just shown this simply here. What you need to do is create a lower triangle or an upper triangle around the force. The condition is you need to create the base and perpendicular of a triangle, or you need to create a right triangle. Then you can resolve the force into two components. One will be parallel to the x-axis and the other parallel to the y-axis. So the lines numbered 2 are the ones parallel to the y-axis, and those lines numbered 1 are the ones parallel to the x-axis. You don't have to create both of these. You can either create the one end below or the one above the force. So in this figure, the x component of the force is 1, that is x component of force F1x is F1 cos 30, which is 40 into cos 30, 34.64 kilonewton, and the y component shown as 2 is F1 sin 30, that is 20 kilonewton. You can check it by yourself. So it is as simple as that. Just take the cos component of the angle, multiply with the force, and you will get the x component of the force, and take the sine of the angle, multiply with the force, you will get the y component of the force. The resultant of these two forces will be 40 kilonewton acting at 30 degree. So that is the concept. You resolve the force into two components so that the resultant force of those two components will be the original force. You can either create a lower triangle or an upper triangle. In fact, you are creating a parallelogram, or you are repeating the parallelogram law here, or the triangular law here. You create a triangle, resolve the force into two. Let's see if we can apply this theorem into a more complex system of forces. Don't get confused seeing this figure. I'm going to explain it to the very detail. In the figure, you have got your x-axis and your y-axis, and a force acting at 30 degree with the x-axis of 40 kilonewton, and a second force acting at 120 degree with the x-axis. The force is 15 kilonewton, and a third force of 20 kilonewton acting at an angle 240 degree with the x-axis. We have already resolved the first force, the 40 kilonewton, into two components, the x component and the y component. So we have got 34.64 along the x-axis and 20 kilonewton along the y-axis. So what we are going to do now is resolving the other two forces. So let's consider the second force of 15 kilonewton acting at an angle 120 degree with the x-axis. Again, that's been shown as a parallelogram. Here it's a square or a rectangle. You can either create a lower triangle or an upper triangle. So just find the cos of the angle, that is 120, multiply that with the force, you will get the horizontal component or the x component, that is F2 cos 120, that is minus 7.5 kilonewton. And because this is a minus sign, there is a negative sign, which implies the force is acting along the negative x direction, or that is from the origin the force is acting towards this direction. If that was a positive, then it must have been in the positive direction of the x-axis. Now to find the vertical component or the y component, simply find the sine component, sine of this angle, multiply that with the force. So you have F2 sine 120, 12.99 kilonewton. Now going to the third force, you have 20 kilonewton acting at an angle 240 degree with the x-axis. So that's shown here again, 20 kilonewton acting at an angle 240 degree with x-axis. What you need is find the sine and cos of 240, multiply that with the force, you will get the two components. So cos 240 into F3 will give you the x direction component or the component along x-axis, and sine 240 into the force will give you the vertical component or the component along y-axis. So minus 10 and minus 17.32. Now to find the net forces along x and y-axis, what you need to do is you need to find the sum of all the forces along the x-axis and all the forces along the y-axis. So that will give you the resultant forces in x direction and y direction. So the net force in x direction is Fx is F1x plus F2x plus F3x. So we have already calculated F1x is 34.64, F2x is minus 7.5 and F3x is minus 10. So the net force along x-axis is 34.64 minus 7.5 minus 10, that is 17.14 kilonewton. And for the net forces in y direction, you have Fy is equal to F1y plus F2y plus F3y. So we have already calculated the y component of first force as 20 kilonewton, and for the second force 12.99 kilonewton, and for the third force minus 17.32 kilonewton. So the net force is 20 plus 12.99 minus 17.32, that is 15.67 kilonewton. You can check it out by yourself. Now the resultant force is, you have got a resultant force in x direction and a resultant force in y direction. So if you draw the forces as a vectors and then find the resultant of these forces, then what you're going to get is the net resultant force of this entire force system. So that's what we shown here. You have got an x component of 17.14 and a y component of 15.67. So you can draw the vector and find the resultant. That is graphical method, and if you want to do it analytically, and then you can also find the angle simply by measuring the angle between the force and the x-axis. You can find the direction of the force as well. So you have the base and perpendicular of a right triangle, and you need to find the hypotenuse. So the resultant force will be square root of, if you consider this as a right triangle, this side will be square root of x square plus y square, where you have x 17.14 and y 15.67. So the resultant force is 17.14 square plus 15.67 square and the square roots. That gives you 23.22 kilonewton. And to find the theta or the angle or the direction of the resultant force, you have tan theta is y by x, that is y divided by x. You know it's 15.67 and 17.14 for y and x. That give you 0.914, and the theta is tan inverse of 0.914, that is tan inverse 0.914 is 42.43. So the angle or the direction of the resultant force is 42.43 and the magnitude is 23.22 kilonewton. You can try this example by yourself to make it thorough.